going to talk about black holes, and the first portion we talk about event horizons. Uh, in lecture 15, it was before we went on to uh, digress to talk about the GR tensors. We talked about geodesic of massless and massive particles, light and planets, in the Schwarzschild space-time. Okay. Remember, in the solar coordinate system, the GR corrections are this ratio is very small, on the order of 1 part a million. But now we're going to talk about the GI effects are huge. So we talk about the Schwarzschild black holes. Uh, the point is that treatment of space and time relativity should be on equal footing, and so the proper arena is space-time. Gravity is the structure of space-time, and the gravity of black hole is so strong that space-time is so warped that this ratio, Schwarzschild radius to the distance in the problem, is order 1. And you will see the effect of this curved space, the extreme curving, is making the rho space and time are interchanged. Of course, I'll explain what I mean by this. So really, in black hole, we see the full power and glory of Einstein's GR. Well, first talk about singularity, Schwarzschild space and time. Basically, we'll talk about the metric, Schwarzschild metric, and inverse metric. And you can easily check that they are singular at r, and r, 1r equal to Schwarzschild radius, as well as the polar angle 0 and pi equal to pi. Now, polar angle equal to 0 pi are coordinate singularities because they are associated with choice of spherical coordinates. They're not physical. Do not blow up in physical measurements. There's no physical measurement. Let's say that 0 pi, the measurement will blow up. So they can be removed by coordinate transformations. However, the r equals 0 singularity is real. This is not surprising, as the Newtonian gravity potential goes like 1 r for a mass, point mass, so already has this singularity at r equals 0. Now, what about the question? What about the Schwarzschild surface? It was what r equal to Schwarzschild radius. This is also a coordinate singularity. For example, if you calculate the coordinate independent quantity contracting the Riemann tensor with all these transits, so it's a scalar, and so independent coordinates. And this quantity shows a singularity r equals 0 as expected, but there's no singularity at r equal to r star. Okay. So therefore, so suggests this is this coordinate singularity. So here we show singularity simply because we're working the Schwarzschild coordinate system. So it's not physical, so it can be transformed away by suitable choice coordinates. For example, we can talk about Kruskal and the coordinates. While physical measurements do not blow up at r equal to r star, that does not mean that the surface is not special. It is actually something we call event horizon, which separates events that can be viewed from afar from those cannot, no matter how long you will wait. That is, r equal to r star surface is a boundary of region from which it's impossible to send out any signals. So this is a boundary communication, much like Earth horizon is a boundary of a vision. And event horizon is a one-way barrier. Any time like or no world line can pass only inwards. Particles light ray cannot move outward. So what we're going to do, we can illustrate this by time measurement across the event horizon. We show that while the proper time crossing of the crossing particle is perfect finite, the far away observer sees this crossing takes an infinite amount Schwarzschild coordinate time, Schwarzschild coordinate time. There's no signal sent from event horizon or its interior can reach an observer far away. To show that the local proper time is perfect fine when it goes across the event horizon. Let tau be the proper time measured in the surface of a collapsing star. Okay? Or you can say, alternatively, the time aboard a spaceship that's traveling radially inwards. Okay, that's the same thing. We have this energy balance equation for particles mass in Schwarzschild. When we talk about Mercury's planet, we have this energy balance equation. The radial kinetic energy, rotational kinetic energy, potential energy is equal to total energy. We can simplify by picking the appropriate, simplify this by picking the constant motion, so that's so that the L equals 0 and the total energy equals 0. Okay, our different respect to proper time. And so what we can do, we can divide by c squared and 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 by divide by c squared, multiply 2 and divide by m. So therefore, this becomes this term divide by m, so small m disappears, and divide by c squared and multiply 2. Then move to the other side. Okay. Now, but 2gm over c squared is just the Schwarzschild radius, so this is simply the Schwarzschild radius divided by r. So in other words, if this equation tells us that c d, take the square root on both sides, c d tau equal to, for the side, is r over r star square root. Okay. And the plus sign corresponds to the exploding star or an outward bound spaceship, and the minus sign corresponds to a collection star or an inward bound starship. We pick the minus sign, so it's inward, and then we integrate this this relation. So what we find that the proper time is a function for r, okay, is perfectly smooth. It just goes like this, starting from the reference point. Okay. So, and it takes a finite amount of proper time after crossing the event horizon to r equals 0. But on the other hand, even though the proper time we show is finite, the coordinate time blows up at the event horizon. So previously we used the proper time expression the with respect to the proper time, and is r dot is equal to minus c r star over r. Now we're interested in the differential respect to coordinate time, okay, and what we can do is we can use it. We already know r dot by dividing this equation by d tau, both numerator and denominator. Numerator divided by d tau, of course, is just r dot, and the coordinate time divided by d tau is simply t dot. Okay, we already have r dot. Okay, but t dot, that's simply the particle energy. Remember, t dot 1 minus r is equal to kappa over c. Kappa is the particle energy. So therefore, and also the script e is related to kappa in this way. So if we set script e equals 0, as we're going to do, and which means kappa equals to c, okay, and because the non-relative energy is E over mc is the kappa equals c, so therefore it's equal to mc squared. It's only rest energy. So anyways, we drop a probe from infinity from rest, and it goes faster and faster towards the. So now we dr dt is written as r dot t dot. R dot is this part, and 1 over t dot is this. So so we have the expression of dr dt, and again we can integrate. Okay, integrate this differential relation. And but you notice now dr has this 1 minus r star of r, so therefore it blows up at r equal to r star. And so instead of the proper time would show last slides is smooth, and the coordinate time h blows up. Okay? And for r very close to this, you can this become you can simply just take this become the log term. Okay? So it takes infinite amount of coordinate time to reach the Schwarzschild surface. So therefore, a distant observer sees a collapsing star slows or to a standstill, in which the light sent from getting closer will take infinite amount of coordinate to reach us. So therefore, a distant observer sees a collapsing star slow down to a standstill, because it never sees going across the horizon because it takes infinite amount of time for it to reach. And then we're looking at all this saying that we have an infinite gravitational redshift. Okay. And remember the coordinate time and the proper time relates d tau is equal to square root g00 dt. So dt is equal to this. Now we have, so this the time interval, you take infinite amount of time interval to pass between the peaks, reaching to reach the faraway observers. Okay. So the time interval blows up. And then we remember we talked about curved space-time in terms the effect leads to gravitational redshift. So the frequency ratio is given by the G00 ratio, and in our case is the G00 is equal to minus 1 r star r. So therefore, when the emission point reaches r star, the frequency goes to 0, which means that, or another way to say, the time interval for the received light blows up in infinity. So it takes infinite. So therefore, there's an infinite redshift. So therefore, no signal can be transmitted from a black hole. Nothing. Okay, stop here.